Okay, so we're going to be looking at vectors again a little bit, but this time leveled up slightly. So we're going to be looking at vectors in 3D. In order to consider vectors in 3D, we want to make sure we've got a good grounding in the correct notation and terminology for the most basic things in 3 dimensions. So that is points in 3D space and distances in 3D space. So it's a fairly basic setup lesson for now, so it shouldn't be anything too difficult, but we just want to make sure you 100% understand everything within this lesson, and that you've effectively got a full grasp of how 2D extends to 3D. And I use the word extends because, to be honest, 3D is not that different from the two-dimensional case. It is more like you're taking all the equations and various formulas and you're extending them. You're just adding more detail in order to get them to work for 3D. So before we launch into that, let me just bring up the sort of prior knowledge check. This is nothing too difficult. 1 and 2 you can get done in a minute really, and then just have a go at 3 just to get yourself back into the zone of working with vectors. So this is sort of just basic stuff that you should be comfortable with, but get that done first, because we'll have plenty of time to go through the new content. So have a quick go at that first. Pause the video now. Okay, and when you're ready for the answers, just to double check, there they are. Okay, so let's look at our first topic for the lesson, which is simply 3D coordinates. So the best way to describe the 3D coordinates is probably to just briefly remind ourselves of how we're looking at 2D coordinates. So we generally take a two-dimensional plane as being divided into 2 dimensions, and we label the values of positions in those dimensions with x and y by default. Okay, right angle here, and a generic point. If I just take any position there in the xy plane, I can label that with a position. Let's say this is x1, y1, for example. Okay, so using the ones, I'm just saying this is the first point I've placed on the plane. So for example, if I put an additional point, I would call this x2, y2, for instance. Okay, so the point being that x and y are the variables label, and by adding this subscript of a number, I'm saying this is a constant. So x1 and y1 has some value, and x2 and y2 has some other value. Okay, cool. All right, that's nothing new, pretty obvious really, but that's the two-dimensional case. So now let's sort of redraw all this as the 3-dimensional case. Now obviously keep this in mind as I draw this. Paper, and in fact this is not paper, this is a computer screen or phone or tablet you're looking at, is a 2-dimensional surface. So already at this point, whatever I'm about to draw, I'm not actually drawing a 3D thing, am I? I'm pointing out the obvious here, but I'm in some sense drawing what we'd call a projection, or less technically a shadow of a 3D object, right? So this 2D representation of points that I've just drawn here, this is exactly what it looks like. But what I'm about to draw now is not actually a 3-dimensional thing. It's a representation of 3D space on a 2D surface. So the way that's usually done is to take a sort of, I suppose it's called isometric drawing. I'm not really familiar with how you label these sort of 3D drawings, but this is effectively what it looks like, and hopefully in your mind you can interpret that this represents a right angle here, and then I suppose there's a third right angle here as well. Okay, so you've got 3 right angles there going on. Okay, so it's kind of like I've taken the XY axis and tilted it a little bit towards me, and then I've drawn on a third axis going, you know, through perpendicular to both of those, and I'm going to call that one Z. Okay, so this is my sort of 3D space. Again, like I say, if you just look at this flat on a page, it looks kind of like, oh, that's about 60 degrees, that's about 60 degrees, but that's not what I've done here. This is a projection of a 3D space. Okay, so these are actually 90 degrees. Let's then draw our generic point. Okay, and we are sort of in a zone of, you know, obviousness here, I guess, but generally the first point I could call x1, y1, and z1. Okay, and these will have 3 values. So for instance, and now here's where it gets hard to draw. Let's say I went to position, let's say this is position 5 on the x-axis. Let's say I've got position, I don't know, 2 on the y-axis, and let's go for position 3. And it's very difficult to draw, but let's give it a go. It's kind of like I've gone, if I go 5 along x, so I'm at the origin, I'll go 5 along x, then let me go upwards to sort of line up with this 2, and then I'm going to go inwards to line up with that 3. So it's almost like I'm drawing a cube. I just finished that cube off. It's kind of like I've drawn a cube there. Hopefully that kind of makes some sense. At this point here, on that cube, that would be 5, 2, 3. Okay, so you can, in a similar way to, you know, how each point in the 2D space, it kind of marks out a rectangle, right? So that's one rectangle. Here's another one. And, you know, the points where those rectangles touch the axes, that's the coordinates. You know, so for example, this one here, that's the x1 and that's the y1. In that similar sense, analogously, you extend that to 3D, and it's not rectangles you're drawing, it's, well, I suppose I should call it cuboids, not cubes. So you're drawing cuboids, and the corner, the far corner of that cuboid, the one opposing the origin point here, the far off corner is the point that you're interested in, and then the lengths of those 3 dimensions describing the cuboid correspond to that point. Okay, right, so that's 3D coordinates. Now let's talk about the distance of a 3D point from the origin. In fact, let me just borrow the previous diagram I drew. Okay, so I've got this one here. That point, 523, the 523 point, how far is it from the origin? So now if I can, I'm just going to draw a straight line from the origin to the point 523, like that. So remember, that line is sort of moving all the way through 3D space. It's the sort of longest diagonal of the cuboid. And the question is, you know, what is the length of that? Now, in some sense, no, let me not over confuse you. You can try and derive the formula yourself. But with a bit of Pythagoras, we can end up getting the same method for finding the distance of this point from the origin as for 2D space. In fact, let me just go back and borrow the 2D space version as well. Okay, so for 2D space, we would say, right, if I just focus on the x1, y1, in fact, let me give it a specific point. Let's just go with 5, 2, keep it simple. So let's say that's 5, that's 2, and I'm going to mark that point there. And then the distance of that point from the origin, that's the red line, okay, the long diagonal. In that case, the working is, well, it's Pythagoras, right? So you're going to say 5 squared plus 2 squared square rooted. So the length of that thing is this. Okay, And similarly, and it's not just, you know, magic, you can work it out by doing multiple versions of Pythagoras, by considering a few different triangles, but before you consider the red line. See if you can derive it yourself. But in this case, you're going to do 5 squared plus 2 squared plus 3 squared and square root it. Okay, so it's nice and simple. So if you think about how this extends, in some sense, this 2, this squaring, and the square root have nothing to do with the fact that it's 2 dimensions. The only sense in which the number 2 comes into this formula relating to 2 dimensions is the number of terms. So the number of terms is what's relating to the dimensions. Here I've got 5 is my first term, 2 is my second term. It's a 2-dimensional expression for distance. Here I've got 3 terms, 5, 2 and 3. So this is the 3-dimensional expression for distance. But square root and squaring, it's always the same thing, right? In some sense, if you think about 1 dimension, let's say it was just, you know, a line, 5, does the rule work? Well, if I square it and square root it, I mean, ignoring the fact that you can have negatives, which we've ignored in the other versions anyway, you just get 5 again. So yes, indeed, you know, if I give you a line of length 5, you square its distance and square root it, you get its distance again. So it works for 1 dimension as well. Okay, so it's always squaring and square rooting, and then summing the components of the dimension. So this is how we find the distance of that point from the origin. Let's then look at an official example. Okay, so there's our point, 4 minus 7 minus 1. I'm just going to point out that in the case of negative values in the dimension, what that means graphically is you're just doing what you would do analogously in the 2D case. You're just going to extend the line, the axis line, beyond the crossing point. So in 2D, you know, these are our positive values, and then the negative ones are just below the origin. And likewise with the horizontal x-axis, the negative values extend out here. In the 3D case, it's almost like you turn your, instead of turning 2 lines into sort of 4, it's like you've turned your 3 into 6. So you've got the vertical y-axis extending below, then I mean, it's hard to use the word horizontal here, but let's say the x-axis then extending through the origin here, and the z coming back this way. So these dashed lines represent the negative parts of the axes. Having said that, though, we don't really need to consider the graph for answering this question. We can just use the formula. So we're going to take 4 squared plus minus 7 squared plus minus 1 squared and square root it. What does that give us? See if you can beat me in your head. Uh, 66 divided by 2 is 33, so that's 2, 3, 11. I don't think we can make that any simpler, really. Root 66. Okay, so that's the distance of that point from the origin. Okay, that's that red line, effectively. This red diagonal line from the origin to that point. Okay, now let's talk about the distance between 2 3D points. Let me bring the graph across actually, just so you've got a sort of a visual sort of guide to just keep in mind. Okay, so let's say you've got 2 points floating out there in 3D space. You know, let's say these 2. Again, it's hard to know exactly where they are based on the image because this is just a projection of 3D space. And we're just asking, what is that distance between them there? Okay, now let me change that actually, let's say a green line. Okay, so I want that green distance. Now the thing is, if I know the 2 points, then I can work out their distances from the origin. Okay, and then using your knowledge of vectors, you can just say, well, you know, let's say, I don't know, let's call this point A and, oops, let's call that one point A and this one point B. And let's say little a is the actual red line vector to that point. Well, if you just do minus a to B, you'll get the length of AB, won't you? So it's the same as 2D as the 2D case. The size of AB, the vector connecting those 2 points, is going to be the same as the size of doing minus A and then plus B. Or in other words, writing it a bit more standardly, B minus A. Okay. How does that translate then into a formula? Let's say I've got 2 points in 3D space. Let's call them x1, y1, z1. That's my first one. That's effectively my A point. And then x2, y2, z2. That's effectively my B point. Let's remove that for a moment. So 2 points there have, how should I phrase this? Let's say have a distance between them of, and we're going to take the difference between them. So we'll do x1 minus x2, y1 minus y2, or you could say x2 minus x1, y2 minus y1, and so on. The order doesn't matter. Why not? Because we're going to square them, and then we'll square root them. Okay, so this is like my A minus B, and then taking the size of that. So doing one minus the other, and then we're squaring the components and square rooting them. Oops. Okay, so that is the distance between two 3D points, okay, which makes sense. No, it's an extension of the 2D case, where you take the difference between the 2 points and then find the magnitude of that differenced vector. Okay, let's look at a specific example then. So I'm going to say I've got 2 points 1, 3, 4, a point 8, 6, minus 5. Find the distance between them. So I'm going to do one minus the other. The order doesn't really matter. And we'll get minus 7, minus 3, 4 minus minus 5 is 9. And I want the magnitude of that. So let's actually just add it to our equation. I want the magnitude of the difference, which is the magnitude of this, which is equal to minus 7 squared, plus minus 3 squared, plus 9 squared. Square rooted equals, let me check that on the calculator. So I get the square root of 139. Okay, done. You can work out, what that is as an actual value. Oh, it says to 1 decimal place, doesn't it? I probably should work it out then. Let's see, square root of 139. It's 11.8 to 1 decimal place. Cool. Oh, another example. Right, this time with an unknown. So you're given 2 points, and the z dimension of one of them is unknown. You're just told it's k. However, you're going to find that unknown because you've been given information. The distance between the 2 points is 3. Find the possible values of k. So the way we're going to do this is to just find the difference as you normally would, and then effectively set up an equation with the information you've been given. Okay, so let's find the difference between them. 5 minus 4, 1. 0 minus 2, minus 2. 3 minus k is 3 minus k. That's my new vector describing the difference between the 2 points. Find the magnitude of that to get the distance between them. That's going to give me 1 squared plus minus 2 squared plus 3 minus k squared, square rooted, and that we are told is equal to the distance, which is 3. So with that information, let's square both sides and just turn this into 1 squared plus minus 2 squared plus 3 minus k squared equals 9 by squaring both sides. And then it's really just a case of solving a quadratic, isn't it? Because you've got 1 squared plus 2 minus 2 squared is 5. Plus, should we multiply out? Maybe we should multiply out. Test. So if we do the multiplying out, we'll get k squared minus 6k plus 9. Okay, and then the 9's cancel nicely, so we can get rid of those. And then if we factor the left-hand side, which is nicely possible because of the nature of the question, we've got our two values, k equals 1 or k equals 5. And these are the only two possible values which we get out of the information we were provided. The reason it's not 1, you need to take into consideration sort of the geometry of what's going on here. I think the best way I can sort of get it to be visualized is to visualize the 2D case. Oh, is that possible? Yeah, let's visualize the 2D case, and then you just need to extend that to the 3-dimensional case. So the 2D case of this would be, you fix one point, let's say this one. Let's go with 5, 0 and 4, 2 actually. So let's reduce it to a 2D case by just knocking off sort of one of the dimensions. So let's go with 5, 0 and let's go with 4 k. Okay, so we're just inventing a new question. The numbers don't matter. So just to make that clear, I'm going to move that down here. So let's say it was this. Okay, and let me just block off the rest of this stuff because it's unrelated to what we're doing now. This is our little thought experiment bubble. So those 2 points, if I plot them, 5, 0 will be here, say, well that's 5, and 4k, well if that's 4, and k is allowed to freely move, so 4k is somewhere on this dashed line. And if I then told you the distance is 3 between them, you could probably imagine that, say, in this top part here, as I move along that dashed line, there is a specific instance where I'm exactly 3 away from this x point. Let's say, you know, the scale isn't important. Let's say it was something like that. Let's say that's 3. In which case, whatever value we get for k here on that red x, that's a possible answer. However, you can hopefully see that there'll be a second answer, which would be whatever the value is down here, where this is also a distance of 3 away. Okay, so in 2 dimensions you'll get these two answers, and again it's the same in 3 dimensions. That value of k gives us enough information to narrow it down to 2 possibilities, and hopefully you can sort of visualize this specific situation, 503 42k. Try and visualize that in a 3D axis in your mind, and it has to really be in your mind because on paper it gets a bit too difficult to draw. Okay, if you can do that, then you know you're getting somewhere to being able to answer these kinds of questions more easily. But in terms of the calculation, it's just what we've got on the page. K equals 1 and k equals 5. Right, so let's do some actual questions now for yourself. As usual, I'm going to show you questions and then give you the answers. So do try them first before you then unpause the video. So this first set, really simple, should take you literally a minute. They're both basically the same question. 2 is a bit interesting because you've got, you know, the same value 3 times. I suppose that's mildly interesting, but give that a go. Pause the video now. Okay, and then quick sanity check to make sure you're doing this right. here are the answers. So presumably, I suppose, I'm just going to make it blurt out a statement. You can agree or disagree. If that was 3/8, would this have ended up being 8√3? I suppose. Yeah, that seems to be the general consensus. Okay. This question here, this one's repetitive, so you don't have to do all 4 parts unless you feel like you want the practice. So that's your option there. Do at least 2 of them. If you feel like you're, for whatever reason, needing to have a bit more practice, that's totally fine. You can do all 4, but pick 2 from here and give those a go. It's distance between 2 points. And then we'll check our values in a moment. Pause the video now. Okay, and then the answers are here. Right, so now it starts to get a little bit more problem solving style. Again, I've put these 2 questions together because they're extremely similar. So you can pick one, or again, if you want a little bit of extra practice, you've got the time, you can do both, but do at least one. In this case, you've got 2 points, 1 unknown value. Can you find the unknown value given the distance between them? Okay, should take you a couple minutes. Pause the video now and give that a go. Okay, and there's our values. And to end with, to practice your sort of visualization of these 3D, points, these 3D objects in your mind. Here you're given 3 vertices of a cube, not a cuboid, a cube, and you're asked to find the coordinates of the remaining 5 vertices. So that's all about visualizing the space. Perhaps you want to draw a diagram for that, probably helps. And then part B is a little bit of a thought experiment. See how you do with that. Definitely try this without checking the answers first. When you're ready, pause the video now. Okay, and there are your 5 other vertices of the cube. See if you got all of them absolutely right. Order doesn't matter, of course. And then the ant is walking, was it 6√5? Is the shortest possible route. Shame it doesn't give you the visualization of the route, but if you've got the right number, presumably you've got the right route. Okay, cool.